Now this is the part 1 video on astronomy and cosmology, and this is a new topic in the 9702 A-level physics syllabus, and my videos are going to be structured in such a way that the part 1 video is going to answer the objectives on standard candles. The part 2 video is going to look at stellar radii, and then the part 3 video is going to look at cosmology, that is the Big Bang theory, as well as Hubble's constant. Now please remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Hit the bell notification so that you get alerted of future videos. Without much further ado, let's get started. Right, so just to lay a background to this topic on standard candles, we have got to start off by defining what is astronomy and what is cosmology. Now, astronomy is the study of everything in the universe. It includes the determination of the nature of things on a small scale, such as the composition and evolution of individual stars, planets, interstellar gas. So when you talk of interstellar, it just means in between the stars. Stellar would then refer just to the stars. So interstellar gas, building to include the makeup galaxies and the galaxy clusters, and finally to understanding things on a larger scale. Now, a group of stars is called a galaxy. So we're going to be studying galaxies. Okay, so galaxies are found in the universe. So that's all about astronomy. Then in cosmology, we are going to be looking at the origin and evolution of the universe itself, the Big Bang theory, and the origins of the universe. That is, so it's a scientific study of the large-scale properties of the universe as a whole. Now, cosmology is a subsection of astronomy, and it deals with the nature of the universe itself, the beginning, the early history, and the current state, and eventually the end of the universe, if ever they. Right, so when we look at the night sky, this is what we observe. We observe these stars, right? Bright stars. So it's called a bright sky, bright night sky, that is. So you find red stars, blue stars, white stars everywhere you go. So you see that's a white star over there, then the blue star, and so forth. So then when we do this, we tend to have some questions, and the questions are: how far are these stars from each other, or how far are the stars from us? What is the radius of each of those stars? Are they moving? If so, how fast are they moving? And when we do so, remember our topic on length and time in the AS syllabus. So we need, as physicists, to measure length and then to measure the time. So length and time, which means these are two fundamental base quantities. So we can then deduce the speed, which is a derived quantity from that. So is there evidence, again, of the fact that this universe is expanding, and what are the implications of an expanding universe? So we're going to look at each and every one of these. In this video, I'm going to stop on light, that is standard candles only. Now, all stars do not look the same. They differ in brightness and color. Now, remember, when you talk of the brightness, we are talking of the intensity, and we are also talking about the amplitude. So that's all related to the power. If you revisit your AS syllabus, when we talked about the relationship between intensity, amplitude, and the power, right? So that's this topic here. We are also going to look at, so when we talk of the intensity, we're talking about that, the power and the amplitude, etc. And we also look at the colors of the stars, like we talked about, which are directly linked to the wavelengths, right? So the wavelength is linked to the color of those stars. So this is in the EM spectrum, that electromagnetic spectrum. So like I said, that the stars do not have the same brightness and color. So the stars that tend to have the blue color, they tend to be the hot ones. Okay, so it's if you take a filament lamp and then you heat, like you pass current in it, so as it starts to glow, it starts reddish, which means that it's not hot enough. So as it starts to get hotter and hotter, the color changes to orange, and then it changes to bluish, and then finally it will be white. So those white stars that you're seeing, they just means that they are emitting light of such wavelength, and they'll be very hot, the hottest stars. Now the stars are not all the same distance from us, and they do not emit the same power. The sun, as you know, that's our closest star, and the second nearest to us will be the Proxima Centauri, and it is 4.0 times 10 to the power of 16 meters away. Now, to express such large distances, that is distances of the order of 10 to the 16, astronomers tend to use the alternative unit for distance, which is called the light year. Now, the light year is not in the 9702 syllabus, but it is in the IGCSE syllabus. So just to recap on what you covered in the IGCSE syllabus, a light year is just the speed, it's the distance traveled by light in a vacuum in a time of 1 year. So we know that distance is equal to speed times time. So 1 light year will be equal to the speed of light in a vacuum times the 1 year in seconds. So speed times time. Now the speed of light in a vacuum is 3.0 times 10 to the power of 8. And then the 1 year in seconds will be 365 times 24 days times 60 times 60 minutes and 60 seconds, which come to be 3,600. So 1 light year will be 9.5 times 10 to the power of 15 meters. Now going back to our next nearest, the second nearest star to us, the Proxima Centauri, we find that it's 4.0 times 10 to the power of 16 meters away, which is just 4.2 light years away. So this means that light that comes from Proxima Centauri is going to take 4.2 years to reach the planet Earth. Right. Then I'm going to talk about luminosity and radiant intensity. The brightness of a star is related to its luminosity, assuming that the power from the star is uniformly radiated through space. And remember, this power is being radiated in all directions, so it forms sort of like a spherical view in 3-dimensional. Also, we are assuming that there is negligible absorption of this radiated power between the star and the Earth. The observed intensity is known as the radiant flux intensity, and it is given the symbol F. Luminosity is given the symbol L. Okay. So the radiant flux intensity, is defined as the radiant power passing normally through a surface per unit area. So that is at 90 degrees to the surface. So radiant flux intensity is equal to the power of a star divided by the surface area of the sphere that it produces. So the power of the star is its luminosity. So don't be confused. Luminosity and power have the same units. Just means the same thing. And the surface area of the sphere is 4 pi d squared. Okay, so please don't confuse this d squared with diameter. It just means the distance that the star is away from the Earth. So therefore, F, the radiant intensity, is equal to L, luminosity, over 4 pi d squared. And the units of radiant intensity is watts per square meter. For a given star, the luminosity is constant. So according to the equation, the radiant flux obeys the inverse square law with distance d. So doubling the distance from the center of the star, which means that the F would then reduce by a factor of a quarter. So as you can see from this, this is D. So if you double the distance, you find that the intensity decreases because light is traveling a further distance. So it reduces by a factor of a quarter. Now this table shows a summary of luminosities of various stars. Now starting with our own star, that is the Sun, which is closest to us, its luminosity is just given this symbol 1.0. Now 1 of this unit of luminosity is equal to 3.83 times 10 to the power of 26 watts per square meter. Right, so from the table it can be observed that the brightness of a star is linked to both its distance from the Earth and its luminosity. So this is the distance from the Earth, and then this is the luminosity, right? So as you can see, this one, the distance is very small, the luminosity is very small. The distance large, luminosity, the luminosity also increasing. But there is also the fact that the temperature has something to do again with this, which we're going to study a little later. Okay, but for now, you just have to know that the brightness of the star is linked to the distance from the Earth and its luminosity. Now, if you take Canopus, it is expected to be bright at night because its luminosity, because it has got a very high luminosity, as you can see, 1100, although it has a distance of 310 light years away from us, its luminosity is very high. So we expect it to be very bright at night. But when you look at a star such as Alpha Centauri, its luminosity is 1.5 meters, 1.5 the units of luminosity there, lux I think. So the star such as that is brighter in the night sky than Arcturus. So Arcturus is 170. This is not because of its luminosity, but the fact that it is closer to us. As you can see, 4.4 light years away. So it's going to be brighter than this one because it's far away. So like I said, so there are other factors that need to be taken into consideration. Right. So if you want to investigate the inverse square law for radiant flux intensity, we have to do this at night to get good results. That is, you need a bright filament lamp and a light meter. So light meters measure a quantity known as illuminance. So we can measure the illuminance using that unit of lux, which is directly proportional to the radiant flux intensity. So you measure the illuminance at various distances d from the center of the lamp, and then since the radiant flux intensity is inversely proportional to the distance squared and directly proportional to the illuminance, a graph of illuminance against 1 over d squared will be a straight line through the origin. So in a laboratory, there will always be some reflection from the walls and ceiling. So the best place for this experiment would be outdoors at night. So that way you come up with a good graph, that is a graph of a straight line graph which passes through the origin. Now let's look at this example. The star Proxima Centauri has a known luminosity of 2.8 times 10 to the power of 23 watts. Astronomers measure the radiant flux intensity on Earth as 1.09 times 10 to the power of minus 11 watts per square meter. Calculate how far the star is away from us. So we're going to use our formula. F is equal to luminosity over 4 pi d squared. Our luminosity is 2.8 times 10 to the power of 23 watts, and then the area is that area of a sphere, which is 4 pi d squared. So it's going to be that. So now making d squared the subject of the formula, it's going to give you that over that, which will get a value of d of 4.52 times 10 to the power of 16 meters. So the distance between the Earth and the Sun is approximately 1.5 times 10 to the power of 9 meters. So this star must be further away from us. As you can see, the order, that's the Sun is 10 to the 9, and then for Centauri is 10 to the 16. In order to measure D, we need to have a reliable way of measuring L and F. This is achieved through the use of telescopes. So these telescopes have diffraction grating on them, and then you can study the spectra, which we're going to talk about later, and then that way you can deduce the distance. We can also find the distance by using standard candles. That is measuring the intensity of electromagnetic radiation of these standard candles that arrive at the Earth. Now, a standard candle is an astronomical object which has known luminosity. So standard candles have been successfully used to determine the distance of widely spread or far-flung galaxies. So there are two well-known standard candles. That is the Cepheid Variable and the Type 1a Supernovae. Right, so Cepheid Variable stars. So these are stars whose brightness varies periodically, and the period of this variation is related to the average luminosity of the star. So by measuring the period, astronomers could determine the luminosity of the star. The radiant intensity at the Earth would then enable the star's distance to be measured. Then observing Cepheid stars in a distant galaxy enables the distance of the galaxy itself to be computed or to be found. So this graph here shows the variation of this luminosity with time, so of a Cepheid variable star. So what is happening here is, just illustrate that. So they measure the luminosity at this stage here. So say the period of this star is about 50 days. So the luminosity will be brightest with the start there, and then after all those days then to be bright again. So as this has been shown, that the radius of the star itself decreases. So this is when the radius is decreased, and then when it is large, that's when we have more luminosity, and then after that period we are going to get brightness again. So such Cepheid variable stars would behave the same, like the same type. We've got type 1 and then type 2, or type 1a and type 1b maybe, of these Cepheid variable stars. So each of them behave the same way. So that is how they came to know about this the luminosity of these Cepheid variable stars. So when the radius of the star changes periodically, the temperature also changes. Okay, the temperature of the stars also change, so that the luminosity also varies. So all Cepheid stars with a given period have the same luminosity, like I said. Then we do have what is called a supernovae, type 1a. So this is what we are going to be looking at. So in a type 1a supernovae, the star implodes, right? So it implodes rapidly towards the end of its life. And then when it does that, it's going to scatter matter and energy into space. So the implosion event may be brighter than the galaxy itself. So that's when they measure the luminosity. So the luminosity of the star at the time of implosion is always the same. So for type 1a supernovae, they tend to have the same luminosity, so that's why they're called standard candles. So this information enables the star's distance from the Earth to be calculated as well. Right, so I'm going to show a video of a type 1a supernovae. Right, so this type 1a supernovae, it emerges from what's called a white dwarf. Okay, so we're going to come to those terms, and then after it explodes, then you get that luminescence that you can see there. So the luminosity is then measured after that. So that's how it works. Okay. Right. So going back to our notes, we're going to look at example number 2. Now, a star has a luminosity that is known to be 4.8 times 10 to the power of 29 watts. A scientist observing this star finds that the radiant flux intensity of light received on Earth from the star is 2.6 nanowatts per square meter. Determine the distance of the star from the Earth. So the first thing that you need to do is to write down what you have. So this is your luminosity, L. Okay, let's go back. Right, so this is the luminosity, that is L, and then F is this one. Remember, F is like intensity measured in watts per square meter. That's that. So that's what you have. So you use the formula. F is equal to L over 4 pi d squared to find D. So to find D, you make it the subject of the formula, which comes to be D squared is equal to L over F, 4 pi F, that is. Then find the square root. So if you find the square root of that, you're going to get a distance of 3.8 times 10 to the power of 18 meters. Right, so I think I'm going to end the video here so that I don't make it too long, and then make sure that you subscribe to the Physics Tips for Cambridge Students YouTube channel. Oh, by the way, I was supposed to go over the objectives that I went through, so I'll just put the objectives right there. Just put the objectives so that you just see what I covered when I looked at these standard candles. Okay, so you now know, in other words, now understand the term luminosity, that it is the total power of radiation that is emitted by a star. You now know how to use the inverse square law of radiant flux intensity, that is F is equal to L over 4 pi d squared. And you now know what a standard candle is, that is an object, astronomical object of non-luminosity. Also, you understand the use of standard candles to determine distances of galaxies. We said that the Cepheid variable stars, they tend to change their luminosity, so they tend to take the values of luminosity after a certain period, which tends to be the same. Now, supernovae, the one type 1a, it happens in distant galaxies, and like I said, they have the same luminosity. So you now know that this is from a distant galaxy, it's a supernovae, and the luminosity after being measured, you find it is the same. So you can find the distance using that formula, F is equal to L over 4 pi d squared. Right, so this is the end of this video. Signing out.